Welcome to section 2.7, inverse functions. All right, before we get started on our objectives, we just got to understand some background information on inverse functions. All right, so the inverse of a relation R is written in as R inverse. So to find the inverse of a relation, we are going to switch the x and y values. Okay, please take note that this -1 in the what it appears to be exponent location is not r to the power -1. It represents the inverse of a relation named r. Okay, so a function has a 1-to-1 relationship if the relationship and its inverse are functions. So a one-to-one function, here's our definition. A function f is a one-to-one function for a and b in the domain of f. If a doesn't equal b, then f of a doesn't equal f of b. Or equivalently, if f of a equals f of b, then a equals b. Okay. So let's look at some examples to hone this in. So in the first one, we have a relation here, which is our set of ordered pairs. So the inverse of R will be the set of ordered pairs where the x and y values are switched. So the point 1, -2 would be the point -2, 1. 2, 4 would be 4, 2. 3, -1 would be -1, 3. And 4, -2 would be -2, 4. Okay. Now, is R a function? Well, in order for it to be a function, every x must match to exactly 1 y. Okay. So in order for it to be a function, every x must match to 1 y. So if I plug in 1, 2, 3, and 4, do I get 1 y? And I do. Now, is the inverse a function? Well, if I plug in -2, 4, -1, -2, would I get only 1 y? No, because if I plug in -2, I'll get the value 1 and 4. Okay. Now, is R 1-to-1? Well, in order for it to be 1-to-1, the function would need to be, the relation would need to be a function and its inverse would need to be a function. So no. Okay. All right. Number 2. So we have our relation, our set of ordered pairs. Okay, let's find our inverse. So it would be 5, 1, 6, 1, -4, 3, 9, 4. Is R a function? No, because 1 maps to 5 and it maps to 6. Is the inverse a function? Yes. So is R 1-to-1? No. And number 3, we have a mapping visual. So the arrows tell you what x coordinate maps to what y coordinate. So we'll take the first one, which is 0, 6 in the relation. So in the inverse, it would be 6, 0. 1 to 2 would be 2, 1. And 11 to 6 would be 6, 11. And I see here that 6 maps to 0 and 11. So I know the inverse is not a function and the relation is a function, so we are not one-to-one. Objective 1, verify inverse functions. So we're going to let f be a one-to-one function, then give g, then g is the inverse of f if the following conditions are both true. So f composition g of x equals x for all x in the domain of g, and g composition f of x equals x for all x in the domain of f. So given a function f of x and its inverse function of f of x, then the definition implies that f composition, the inverse of f of x, and the inverse of f composition f of x would also equal x. Okay. So we're going to determine whether the two functions are inverses of each other. Okay. All right. So we're going to take first f composition g of x. So that's going to be 3. And then we'll plug in g of x into f, and then plus 6. We'll distribute that 3, so we'll get x minus 6 plus 6. The 6's cancel, leaving us with just x. Now we also have to check g composition f of x, so we're substituting f of x into g of x. So that would be 1/3 times 3x plus 6 minus 2. Distribute the 1/3. So that's x plus 2 minus 2, which equals x. So, yes, f of x and g of x are inverses of each other. Okay, let's do b. First, find f composition g. So we're plugging g of x into f of x. So we'll have 5x plus 1 in the numerator plus 1 divided by 5. That simplifies to 5x plus 2 divided by 5, which does not equal x. Okay? So we know right off the bat that f of x and g of x are not inverses of each other. But for those who would have started with g composition f of x, let's see if this also does not equal x. So we're substituting f of x into g of x. So we'll have 5 times x plus 1 divided by 5, and then plus 1. So the 5's cancel, leaving me with x plus 1 plus 1, which is x plus 2, which also does not equal x. Okay? So whether you did g composition f or f composition g, both show that f of x and g of x are not inverse functions of each other. So let's do c. Okay. So we have f composition g of x. So we're taking g of x and substituting it into f of x. So we have the square root of x minus 8 squared plus 8. The square cancels the square root, leaving me with x minus 8 plus 8. So that equals x. Awesome. Now let's check g composition f of x. So we're taking f of x and substituting it into g of x. So we have x squared plus 8 minus 8. All right. We can drop the parentheses so the 8's cancel, leaving me with x squared. The square root cancels the square, leaving me with just x. So yes, f of x and g of x are inverses. Okay. All right, it's your turn. Checkpoint. Determine whether the two functions are inverses. So pause the recording, and once you complete this question, come back and check your answer. All right, here's your answer. So you would have found that f of x and g of x are inverses of each other. Awesome. Objective 2. Find the inverse of a function. So we know how to check whether two functions are inverses, but now we need to look at how do we actually find the inverse of a function. So the equation for the inverse of a function f can be found as follows. For step 1, we are going to replace f of x with y. Step 2, we'll interchange x with y. Step 3, we'll then solve for y. Step 4, we'll rewrite y as the inverse of f of x. And then for step 5, we'll verify that the composition of f composition, the inverse of f, and the inverse of f composition f both equal x. Okay. All right, so for examples here, we're asked to find the inverse function of the following functions. Okay, so let's first do A. All right, so our first step is to replace f of x with y. Our next step is to interchange x and y. So now where there was y, it's now x, and where there was x, it's now y. Now we want to solve for y. So we'll have x minus 7 equals 2y, and then I'll need to divide everything by 2. So then y equals x minus 7 divided by 2. Okay. Then my step number 4 is to write y as the inverse of f. Okay, and so now I have my inverse function. Okay, B. So we'll take f of x, and then we will interchange. Oh, before we interchange, we got to replace f of x with y, and then we will interchange. So now we have x equals y plus 1 divided by y minus 5. Then we need to solve for y. So we'll multiply both sides by y minus 5. And then we will distribute the x to each term. Then we'll get the terms that contain y on one side and everything else on the other. So that'll be xy minus y equals 5x plus 1. Then on the left-hand side, we know that both terms contain a y, so we can factor out a y. And to get y by itself, we will then divide both sides by x minus 1. Then we will replace y with the inverse of f, and that equals 5x plus 1 over x minus 1. Okay. C. All right, we have f of x equals x squared plus 3. So we will replace f of x with y. Then we will interchange x and y. And then we will solve for x. Sorry, solve for y. So we'll subtract 3. And then we will take the square root of both sides to eliminate the square of y. And we will replace y with the inverse of f of x. And that is our inverse function. Okay. Now with all of these, a, b, and c, you would verify them by taking the composition of f and the inverse of f of x and confirming it equals x. Then you'll take the inverse of f composition f of x and confirm that it equals x. If both of these equal x, then you know for certain that your two functions are inverses. Okay, so now it's your turn. So why don't you pause and find the inverse functions of the following 3 functions. All right, here are your solutions for A, B, and C. So for A, the inverse of f of x is 2x minus 4. For B, the inverse of f is x over 3 minus x. And for C, the inverse of f is the cube root of x plus 1 divided by 4. All right, objective 3. Use the horizontal line test to determine if a function has an inverse. So recall that the vertical line test is used to determine whether a relation is a function given a graph. So the horizontal line test then is going to be used to determine whether the inverse of a relation is a function. Okay, so both the relation and its inverse must be a function to be a one-to-one function. So the horizontal line test says that a function f has an inverse that is function the inverse of f if there is no horizontal line that intersects the graph of the function f at more than one point. In other words, if any horizontal line intersects a graph at 2 or more points, the graph will not define a function. The graph will only pass the horizontal line test if any horizontal line crosses it only at one point. So in our examples here, we're asked to determine whether the relations shown represent one-to-one functions. Right? So in order for it to be a one-to-one function, it has to pass the horizontal line test and it has to pass the vertical line test. Okay, so the vertical line test, remember, states whether your relation is a function, and the horizontal line test states whether your inverse function or relation is a function. Okay, so for the first one, we see here that it passes the horizontal line test, so we know the inverse is a function. And it also passes the vertical line test, so we know that this function is one-to-one. Okay. All right. Next, we have a linear line. So if we draw our horizontal lines and our vertical lines, they only touch the graph one time. So we know this relation represents a one-to-one function. So for this relation, we just have points. So our horizontal line, there's no other point on all of these horizontal lines. Then we'll check the vertical. There's no other point on any of these vertical lines. So yes, this is a one-to-one function. Okay. Now for D, vertical lines, to test whether the relation is a function, And there's no vertical line that crosses the graph more than one time, so we know this relation is a function, but is it one-to-one? So now let's test the horizontal. If I draw a horizontal straight through here, I see that it touches the graph 4 times. So the inverse is not a function. So since the relation is a function, but its inverse is not a function, this is not one-to-one. Okay? All right. Your turn. Determine whether the following relations shown represent one-to-one functions. All right, here are your answers. So the first one, yes. B, no. C, no. And D, yes. All right. Objective 4, use the graph of a one-to-one function to graph its inverse function. All right. So what is the inverse of this relation? Well, we know from the beginning of this section that if we're given a relation, which could be a set of ordered pairs, we know that the inverse is going to be the x and y values switched. Okay? So in this relation here in blue, I have some ordered pairs that are present. Okay? And the ordered pairs that I see are 1, 4, -2, -1, 2. What is that? -3, 1, and -4, -2. Okay. So that means the inverse would have the ordered pairs for 1, 2, -1, 1, -3, and -2, -4. Okay, so let's plot those points. So for 1, 2, -1, 1, -3, and -2, -4. And then we can connect those dots. And so now we have our inverse function. So what do you notice about this inverse function? Well, I know this blue here represents f of x, and the red here represents the inverse of f of x, and they seem to be mirroring each other across this dashed line. So that would mean that they reflect across the line y equals x. They're reflections of each other across the line. And that line is y equals x. Okay? So if I have my points f of x and I create my dashed line, the points for the inverse of f are going to be the same equal distance from every point of f on the other side of my dashed line, which is the line of y equals x. So for your examples here, where you are asked to use the given graphs to graph their inverse functions, you can identify your reflection line, y equals x, identify some points on your graph, and the points of your inverse function would be equal distance on the other side of your graph. Okay? All right, so why don't you pause the video and give it a go. Here's our solution. Okay, so for A, B, and C, you could have identified some points, state their inverses, plot those points, and then connect the dots. You could have also drawn your dashed line of reflection, y equals x, and plotted points equal distance from that line. Okay. Either pathway works. All right, objective 5. We are going to use a graph of f in the figure below. Well, objective 5 says graph both the function and its inverse on the same axis, which we kind of did in the previous objective, but the function graph was already given to you. So now we are going to include graphing the function in this objective. So we're going to use the graph of f in the figure below to draw the graph and its inverse function. Okay, so the graph of f here is provided, and we have the ordered pairs -3, -2, -1, 0, 4, and 2. In our upcoming examples, our graph of f is going to be given as an equation, so that means we're going to have to find some ordered pairs. Once we find those ordered pairs, though, we can find the ordered pairs of our inverse by switching the x and y coordinates. So the points on a graph of the inverse of f would be -2, -3, 0, -1, and 2, 4, which you see here in green on the graph above. We have our inverse of f of x at those points with those points connected. Okay, and of course, f and its inverse are reflections of each other over the line y equals x. Okay. All right, so let's do some examples here where we're asked to graph f and its inverse on the coordinate plane. Okay, so we have the graph of f of x here. Now, there are many ways to do this, and I see here that f of x is written in the form y equals mx plus b. So I know my m is 1/3 and my b is -1, which is my y-intercept. If I wanted to find the inverse function, I would have to make f of x y, interchange x and y, and then solve for y. So I'll add 1 on both sides, then multiply everything by 3. So 3x plus 3, and then replace y with the inverse of f. Now the slope of my inverse is 3, and my y-intercept is 3. Okay, so that's one way to do it. The other way is to take your function, f of x, plot some points. So let's start at our y-intercept, which is -1. And our slope is 1 rise over run, so 1/3. So up 1/3, up 1/3, over 3, down 1 to the left 3, opposite direction. Okay, and so I have my graph here. All right, so now if I wanted to plot my inverse, I could take these points and switch the x and y in order to plot the points of my inverse function. Since I already found my inverse equation, I can just use that information to plot that graph. So this is f of x, so I'm just going to label that. So the next one is my inverse. So we start at the y-intercept, which is 3. 1, 2, 3. And our slope is 3, 2. So that's 3/1. So I'm going to rise 3/1, rise 3/1, go down 3/1, down 3/1, 3/1. Okay, and I'm going to connect my dots as close as I can. And this is the inverse of f. Okay. All right, let's do another one. All right, f of x equals x squared minus 4. And we're only going to take the values where x is greater than or equal to 0. Okay. Let's find the inverse function. So we'll replace f of x with y. Interchange x and y. Oops, that's not supposed to be there. There we go. And then solve for y. So x minus plus 4 equals y squared. So y equals the square root of x plus 4. So replace y with the inverse of f. Okay. So the first value is our function, and the first values we're going to plot are going to be of our function f of x, and that is a quadratic. Right? So it has the point for its vertex 0, -4. Because if I plug in 0, I get -4. Then if I plug in 1, I'll get -3. If I plug in 2, because these are all the values that are greater than or equal to 0. If I plug in 2, I'll get 0. If I plug in 3, that'll be 9 minus 4, which is 5. 1, 2, 3, 4, 5. If I plug in 4, that would be 16 minus 4, which is 12, and that's off of my table. So let's connect these points. All right, so those are all the values where x is greater than or equal to 0. Then we have the inverse function. Okay, so I had the point 0. We do the points here for x and y. I had the points 0, -4, 1, -3, 2, 0, and 3, 5. That was for my f of x. So for my inverse function, my points then are going to be the x and y values switched. So -4, 0, -3, 1, 0, 2, and 5, 3. So let's plot those. 1, 2, 3, 4, -3, 1, 0, 2, and 5. 1, 2, 3, 4, 5, 3. Okay. Connect those dots. And we have our inverse function. So this is f of x. And this is the inverse of f. All right. Let's do one more. F of x equals 2x plus 8. So let's replace f of x with y. Let's interchange x and y. Now let's solve for y. And then divide by 2. Okay, so we can rewrite this as 1/2 x minus 4. Then we'll replace y with the inverse of f. Okay, so the slope of my function f of x is 2. My y-intercept is 8. The slope of my inverse function is 1/2. And my slope is -4. Okay, so they're both going to be linear lines. So let's first plot the function of x. So we'll start at 2. Sorry, not 2. We'll start at 8. Our intercept is 8. Our slope is 2. So we'll start at 8. So 1, 2, 3, 4, 5, 6, 7, 8. Slope is 2 over 1. So up 2 over 1. and we have no graph. So now we need to go in the opposite direction. So we'll go down to the left one, down to the left, down to the left, until we have no more graph. Okay. And so now we'll plot our inverse. Let's connect the dots first. Oh boy, where's my line going? Let's try that one again. Much better. Okay. Now let's plot the inverse. So our y-intercept is -4, so that's where we're going to start. Then our slope is 1, 2, so up 1 to the right 2. And then we'll just keep going till we have no more graph. Then we'll start going in the opposite direction, so down 1 to the left 2. And then once we have no more graph, we'll connect our dots. And we now have the points of our inverse function. So I'll label, this is f of x, and this is the inverse of f of x. Awesome. And that concludes section 2.7.